I'd like to acknowledge, first of all, a travel grant that I got through the International Association of Geomorphologists that helped me come here, so I really appreciate that. So I'm going to talk about patterns of Martian deglaciation and periglaciation, which is in a periglacial session, just to confuse you all. I'm really using gullies as a tool here to indicate gullies as well as associated features, just like the last talk was discussing, how we can use these features to determine characteristics of previous Martian climates. And specifically, I'm looking at the late Amazonian. Excuse me. So based on our talk yesterday afternoon, our discussion, I thought I would actually define what the periglacial period is on Earth. It's basically the response of an environment, a landform, a feature, a period of time that is directly conditioned by glaciation and deglaciation. So if you have a period of glaciation and you lose that, you deglaciate the region, there's all kinds of instabilities introduced into the system, and the environment will naturally respond. So this response to deglaciation is broadly described as periglacial, not to be confused with periglacial, which is features or conditions near glacial margins. There's also proglacial, so they're all pronounced around the same way. This is periglacial. So to go in a little bit more detail, the periglacial period itself works by first having a glacier. When you enter a period of deglaciation, that glacier will retreat and you'll expose valley walls, sediment stores that were formerly covered by ice and also supported by the ice. So when you deglaciate the region, the sediment on these slopes will be exposed and not sedimented in any way. So you'll form gullies, as we're talking about here. You'll also form large talus fans. You'll have large-scale rock slope failures. And so as you continue to deglaciate your region, this periglacial reworking will continue to form. And eventually, once the region has been completely deglaciated and these periglacial features are no longer forming, this periglacial period is over. And on Earth, this is enhanced due to the introduction of vegetation. So the periglacial activity that we see is classified by different land systems. So that is, land systems in general are a specific kind of activity that is categorized by a specific feature. So the most diagnostic periglacial landform that we see on Earth is gullies, which is why I'm here. You can see these gullies here in Svalbard. We also have what's generally called slope evolution. This is characterized by anti-slope scarps, which are also called Sackungen in German. I apologize to our German colleagues for that pronunciation. It means sagging. And basically, there are about 12 different formation mechanisms for these Sackungen. There's basically some sort of deep-seated jointing or deformation of rocks, potentially in response to isostatic rebound, that forms these upslope, anti-slope facing scarps. And in addition, we have thermal cycling, which creates gelifluction, solifluction lobes, and polygons, which were just discussed in the previous talk. There's also 3 different land systems on Earth: alluvial, lacustrine, and coastal systems. Since I'm applying this concept to Mars, we're going to just ignore these 3 for now. A key point of the periglacial period, periglacial land system, is that the presence of any of these features alone does not indicate periglacial reworking. So if you just see a gully on its own or a single polygon, that does not mean that we are in a periglacial environment. You need to have some sort of deglaciation in the system that these features are forming in response to have that periglacial period. So we have this periglacial concept. The question is, can we apply this concept to Mars? And specifically, can we use gullies and other associated features to identify periglacial modification on Mars? Maybe you can guess the answer to that since I'm here talking about it. To the uninitiated, this is a glaciated crater on Mars. You can see that there is some sort of concentric fill in this crater, hence we call it concentric crater fill. This is actually debris-covered ice. There's up to kilometers of ice inside these glaciated craters with up to meters or so of sediment on top of the ice, which is believed to accumulate around the rim of the crater and flow downslope into the crater. So these are glaciated craters. I'll use the acronym CCF for concentric crater fill, but I'll try to stay away from using that acronym too much. This is an example of, I would argue, a paraglaciated crater. You can see that there is an example of this CCF, this concentric crater fill inside the crater, but then you have other stratigraphically younger units that are modifying this crater. Since they're stratigraphically younger, these had to form after the period of glaciation. Specifically, there is a suite of features that we see inside the crater. There's a lot going on here, so I'll try to talk not too much about each of them, but if you have questions, please ask me afterwards. The most noticeable are these flat floor depressions with these sharp bounding scarps, which we call Spatula Depressions. Other researchers have called these terminal moraines, which I would not argue with that logic. We call them depressions because we believe that they're formed through the large-scale, fairly rapid sublimation of glacial ice that was in these depressions. Once it's sublimated, you're left with this flat floor, fine-grained sediment covering, and these sharp boundaries. Polygons and what we're calling broad pits, which are similar to those thermokarstic features discussed in the previous talk, are found all around the crater rim here. Those, again, are formed through thermal cycling of a potentially near-surface ice layer. Thermal cycling on daily or seasonal timescales causes fracturing of the surface layer. Those fractures eventually become interconnected to form these polygons. We have gullies, which everyone is familiar with, so I won't go into too much detail here. We see these gullies all around the crater rim on the northern and northeastern portion of the crater. And then we have this other feature, which we're calling washboard terrain, for hopefully obvious reasons. Up and to the right is upslope in this figure here. The sun's coming from the left. So these appear to be upslope-facing scarps, which are morphologically similar to those anti-slope scarps in the terrestrial periglacial settings as well. And this washboard terrain forms at the base of the crater wall and is always associated with gully sediment fans. And we talked about these fractures a little bit yesterday in association with gullies again. So all of these features are stratigraphically younger than the concentric crater fill. I argue, and hopefully you can believe me, that these features all form in some response to the loss of glacial ice and then the response of the crater system to that deglaciation. So therefore, potentially, these features are forming a periglacial period within this glaciated crater. So if you can believe that, we've identified a periglacial period on Mars. So the question then is, what is the distribution and variability of Martian periglacial activity in the mid-latitudes of Mars in other glaciated craters? So what I've done is analyze all of the glaciated craters, all of the craters bearing CCF on Mars. It's 631 craters. I thought that was like a huge amount of anything to have in a database until I saw Tanya Harrison's gully paper with like 7,000 gullies. So yeah, 600 is not that many. But that database is from the Dixon et al. 2012 analysis of different glacial features in the mid-latitudes. And so this is the results of that work. All of the open squares are craters that contain concentric crater fill, so glaciated craters. And then the other features shown here are the different features that are present in each of those craters. So as you can see, there is evidence of periglacial reworking across both the north and the south hemisphere. But the distribution of these periglacial features is not uniform. So we don't see every periglacial feature in every glaciated crater. You can see here that in the southern hemisphere, there are relatively more periglaciated craters, in addition to the fact that there are just more craters in the southern hemisphere than in the northern hemisphere. In addition, we see more gullies in both the north and the south hemisphere than the other features in those craters. And as an aside, I mentioned the washboard terrain. Every crater where we see washboard terrain, we see that feature associated with gullies. So there is some sort of relationship, I believe, between these two features. So feel free to ask me about that afterwards, and hopefully I can answer your question. So what I'd like to do is quickly step through just 3 regions that I've indicated here to show the variability in the periglacial response of these craters. The first location is the Deuteronihilus Protonihilus Mensae region. I apologize if I didn't pronounce that correctly. This is located on the dichotomy boundary. It's a region that's well known for being very glaciated. So again, these white squares here are all of the glaciated craters. And you can see that we don't see many instances of periglacial reworking. There's only about 6 in this whole scene here. So the question is, why are there, in this very glaciated region, why are we not seeing any sort of deglacial response, any periglacial response? And I think the reason for this is that most of the, well, pretty much all of the periglacial features I just identified are forming in and near the crater wall. So this is in the southern hemisphere. Pardon the typo there. This is a 750 meter diameter, 750 meter scale bar down there. You can see gullies obviously form in the crater rim and crater walls. The washboard terrain is always associated with these gully sediment fans. In addition, the polygonal terrain, which was again talked about in the last talk, forms in these crater walls. And what we see in these Deuteronihilus, Protonihilus Mensae craters is that we see that there is relatively more concentric crater fill in the craters. The craters just are more full than other craters, and so we're not exposing enough of the crater wall in which we can form these periglacial features. So in these regions, we're not getting a sufficient amount of ablation in the deglaciation process, or there's too much accumulation to create this periglacial response. In comparison, we can look at the Amazonas Planitia region. This is just west of Olympus Mons. We can see that there are no glaciated craters in this region at all, and indeed very few craters. This has been identified by Fuller and Head in 2002 as one of the smoothest regions of the planet. And so it's then unsurprising that we don't have any glaciated craters. In order to have a periglacial response, you need to have a glaciated crater in the first place. So in this region, the lack of abundant craters and steep slopes has just inhibited ice accumulation in the first place. So maybe that's not too surprising. Finally, we can look at the Southern Highlands. This is a huge expanse of the Southern Highlands where we see a very high concentration of these periglacial features. Right here, this is the highest density of these features in the Newton Basin region, which we've talked about a few times. It has a very high concentration of gullies, as well as these periglacial features. And then we can see this distribution is continued across the rest of the Southern Highlands in this region. And I'll just reference the work from Jay Dixon that I presented yesterday, which, just to review, those authors used a three-dimensional climate model at various obliquity scenarios to model the climate of Mars at various periods in the last million years. And so this is just the summary of the high obliquity period, which was at 625,000 years at a 35-degree obliquity run. And under those conditions, all of the mapped gully locations of the southern hemisphere experienced at least a few hours of conditions that were at or above the triple point of water. And so given the caveats that we discussed yesterday after that talk, it is potentially likely that we did have long periods of melting conditions in these locations. And these locations in the Southern Highlands correspond quite closely to where we see this enhanced periglacial response. So it could be that these melting conditions enhance the rate of periglacial activity in these locations. So just to step through some conclusions, gullies with associated other geomorphic units, my Spatula Depressions, this weird washboard terrain, and polygons, could indicate periglacial modification in the mid-latitudes of Mars. And again, this periglacial response is the environment responding to deglaciation. And periglacial modification itself is variable across the mid-latitudes. You need to have a sufficient amount of accumulation and glaciation in order to actually have something to deglaciate. So in Amazonas Planitia, we just didn't have any glaciated craters. If you have a lot of accumulation but not enough ablation, you might be inhibiting your periglacial response just because there's not any crater wall area to modify. And finally, if you have abundant accumulation and abundant ablation, this could apparently encourage periglacial activity. So with that, I will take questions. Thank you.
Richard.
Often in looking at gullies that are polygonized, you will see that only the channel walls are polygonized and the adjacent terrain may not be. What you have here is an ablating, or what you highlighted is an ablating landscape, an ablating glacial landscape. Have you thought about the possibility that what we deem to be para is actually pre, and that what is being revealed is a landscape that was covered over by this glacial LDM, perhaps, and this being revealed once again as the glacial mass retreats?
Yeah, it's a really interesting point, the role of the LDM in this whole periglacial story. Since the periglacial framework on Earth is just an environment that is responding to deglaciation, the fact that you're removing an ice-rich, potentially glacially tied unit like the LDM could suggest that this is still periglacial reworking, the accumulation and ablation of the LDM layer. So it's certainly true, and we do see a lot of these gullies that contain polygons. Joe Levy calls them gullygons, these units. And so there definitely is some sort of relationship between the LDM and the periglacial response in these craters, absolutely.
Paul?
Could you say a bit more about the washboard terrain? It
Sure.
looks very much like Rogan moraine, which is caused by ice expansion. So I was wondering if, as the ice retreats, it leaves a Rogan moraine on the lower slopes.
Yeah, I'll just go back to my slide that has the image of the washboard terrain on it. Here it is. So the washboard terrain always occurs, as I mentioned, with these gully sediment fans. You can see a fan right here. It appears that there is this close relationship with gully fans and the washboard terrain. The washboard terrain is usually stratigraphically older than the youngest generation of fan creation, but there's some interleaven nature of the older gully fan units and the washboard terrain. In addition, both of these units occur in locations near where you have the Spatula Depressions, and so if the depression is here, there's washboard terrain right above that on the crater wall, and then the gully being deposited on top of the washboard terrain. So our model for its formation, again, we're still working with a couple of models. The most likely one, I think, is that the creation of this Spatula Depression forms, as I said, through the sublimation of ice. And this basically is removing the basal support for the sediment on the wall. You're essentially debuttressing your wall sediment. And then added with that is the fact that you have more sediment being deposited on the wall from the creation of this gully fan. I think it just destabilizes the unconsolidated sediments on the wall, and you have slumping down of this material. If you have a subsurface ice layer, that would be a low frictional plane that sediment could potentially slide on top of, so it might make that deformation a little bit easier. But we do see such a close spatial association between the Spatula Depressions and the gullies that I think there needs to be some role of those two features in its creation there. So that's our working model. But yeah, I'm certainly open to other opinions, like this moraine potentially. Yeah.
I can accept that explanation, but I would want to explore the possibility of it being Erosion moraine.
Yeah, I will look into it.
Further, yeah.
I think we should move on to the next talk. So, coffee break. Next talk is by Tanya Harrison.
So I'm just going to start with a little PSA. My map has come up a lot in this meeting, and if anybody is looking to use it, it is publicly available as a layer in JMARS. If you go under the interpreted map section, when it comes back up. So under interpreted maps, 2015 Gully Landform Survey, you can bring it up in JMARS, and you should be able to export it from there as a CSV file. If you can't, feel free to email me, and I'm happy to send it to anybody that wants to use it. But I'm not going to talk about mapping today. Today I'm going to be talking about using thermal inertia of gully fans as a marker for looking for signs of recent gully activity. And this actually started out as a null results study. Based on mapping from my 2015 paper, looking at the correlation between gullies and thermophysical surface units from tests, it looked like that there was a correlation between places where we see gullies and areas with surface properties that were consistent with low dust cover, low albedo, and grain sizes in the 60 micron to 3 millimeter range. We didn't tend to see them in places that were very fine grained or very coarse grained, so pebbles and boulders. So from this, I decided to take a look at thermal inertia measurements at a higher resolution scale to see if we could see any relationship between gullied versus non-gullied walls, both in the same crater and gullied versus non-gullied craters. Was there any consistent relationship looking at these slopes? No. So while I was looking at this, though, we came across something else that was interesting, which will be what I'm talking about for the rest of this. So we all know gullies are active today, and all of the places where we've been able to track down gully activity that's happening today are places where we've had before and after images. So we need two pictures to be able to constrain when this activity is happening. But, and I'm not sure how accurate this map is now, because I think Colin's map had a lot more yellow stars for active places on it. The number of active sites is a few dozen compared to about 5,000 separate sites across the whole planet where we've seen gullies. So we're definitely missing places where there's activity just because we don't have the ability to do repeated imaging of all of these places. So is there some other way that we can try to look for places where even if we can't constrain the date of formation, we can look and see if there's been recent activity in some place? And this is where thermal inertia actually came in handy. So I'm sure everybody in here knows high thermal inertia means sort of rocks and boulders type material. Low thermal inertia typically means, much finer grained material. And if we use GASA as our type example here, this is a really great example because we have lots of gully activity happening in this crater, and it has very large gully fans relative to a lot of other sites on Mars. So this is a place where we can take the pixel size of the Themis thermal inertia data set, which is 100 meters per pixel, and overlay it on top of the images to take a look at some of the structure within these fans. So this is an area that we're going to be focusing in on, where we can clearly see a younger fan lobe that has been superposed on top of older material. And in all of the places where I looked inside of GASA, the uppermost lobes, the youngest lobes, have thermal inertia values that are about 20 to 40 thermal inertia units higher than the underlying lobes. And then the alcoves have the highest thermal inertia values, so the green areas. This is to be expected for the alcoves because it's the least dusty and it has the most exposed bedrock. So zooming in here, we have the youngest fan lobe here. It looks much more hummocky than the older degraded fan lobes. When we look on Earth at thermal inertia or thermal measurements of alluvial fans, we actually tend to see the opposite relationship. The older fans tend to have higher thermal inertias based on studies done by Craig Hardgrove of alluvial fans in Death Valley, just because thanks to fluvial transport and aeolian transport, the fine material gets eroded away and leaves the boulders behind. On Mars, we have a combination of breakdown of boulders over time due to erosion and dust deposition on older fan lobes. So this is my hypothesis, at least, for why we're seeing the older fan segments having lower thermal inertias than the younger fan segments. So mapping out different fan segments throughout GASA, this is of about 60 different segments throughout the crater. There's a transition in the thermal inertia values going from the older fans in sort of the 300 to 360 thermal inertia unit range, and then the younger fans go all the way up to 440. I also did this for Gallup and Triolet craters and found similar relationships, about 20 to 40 thermal inertia unit differences between. I'm only looking at the relative differences between them because there's issues when you're looking at thermal inertia on steep slopes getting absolute values, so I'm not looking too much into the absolute values just yet. We might need to do some more processing of the data to make sure that it's accurate. Changing gears a little bit, we recently found another method by which we can look for signs of recent gully activity using IR spectroscopy from CRISM and CASIS, which is the camera aboard the ExoMars TGO orbiter that's on the way to Mars right now. This is serendipitous because CASIS is actually having their science team meeting in Bern as we speak. So CASIS is the color and stereo surface imaging system. It has 4 color bands that it's going to be imaging with: a blue, a panchromatic, a red, and a near IR. It has a color swath that's about 9.5 kilometers wide compared to the about 1 kilometer that we get with high rise. The resolution is much lower. It's only 4.6 kilometers per pixel, so it's higher than CTX but lower than high rise. And thanks to the unusual orbit of TGO relative to the other orbiters that we have right now, it's going to give us unique and multiple time of day observations across multiple Martian seasons of gullies on Mars. And there was some question about whether or not CASIS might be useful in looking for changes in gullies because of the resolution compared to high rise. And here, Livio Tornabene has made simulated CASIS images by taking CTX images, resampling them to CASIS resolution, and then combining them with CRISM S detector images that have been resampled to the 4 wavelengths of CASIS. And when we look at images covering GASA at different periods of time, we can actually pick out changes in the color. So all the places where we have yellow arrows here are places where we see changes between this image in July 2009 and this image in June of 2011. So if we compare that to the high rise, from talking to Colin, it sounds like all of the changes that are picked up in this IR data set are visible in the high rise grayscale, but they're not necessarily readily apparent. You have to have like blink images or have some kind of topographic change that's noticeable enough for your eye to pick it up. So the red arrows here are places where there are changes that we can see in the CASIS simulated images with those resampled CRISM bands that are not readily apparent in the high-rise grayscale, and then the green arrows are places where we can easily see the changes in both the high-rise grayscale and the CASIS simulated images. Even just looking at CRISM, as Jan showed in his talk, you can actually see some of these larger scale changes at the CRISM resolution. So if we're zooming in on this box here, it's kind of hard to see. So this is a before image. This flow is formed sometime between this image and this image. And then over time, we're actually seeing these starting to fade at CRISM scale, which could be due to dust deposition on top of these features. So thermal inertia differences across different gully fans or different segments of an individual fan might be able to reveal areas of recent activity, even though we're not able to necessarily date before and after unless we have repeat thermal inertia data set coverage, which is a little tricky at the moment. We can at least look for areas where it looks like there's been fresher activity, and this might help us pick places that we should be monitoring, because right now CTX is monitoring about 700 individual sites on, they're trying to do a 4-month basis. It looks like Highrise is monitoring a good majority of those now at this point. But if we can look for these thermal inertia changes, maybe it's something to help us narrow down places to be monitoring more frequently. And we'll be able to hopefully combine CRISM S detector images with these monitoring efforts from CTX and Highrise to help look for maybe more of these changes. And then CASIS, once it reaches Mars orbit, will be able to help in this gully monitoring effort as well at its resolution. And with that, I'll take any questions.
Colin?
Do you have any idea how long it takes for the thermal inertia to reset back to the background?
Yes, so if you take sort of the average dust deposition rates from MER and Curiosity, it ends up being about 2,900 Mars years, so it's relatively quick. Great,
Any
thanks.
other questions? And it's time for a coffee break. I think we reconvene at 2:30, so announcement.
Yes. Can I ask you all, can we convene just in front of the gallery and we can take a group photo of the people who are present at this conference just as a, I don't know, as a yay, we were all here kind of thing. Has anyone got a decent camera? Because I haven't. Good, great. Thanks, yeah, so if everyone's kind of gathers in the library area, we'll get that done.
Welcome to the last session here at the conference, which is about mathematical models. And our first speaker is this is an invited talk, a longer talk, is Dr. Anne Mangenet from IPGP. And she is an expert in mathematical and experimental models of granular flows. And that's what she's going to talk about, and issues of how to detect them.
Okay, thank you. So thank you for inviting me in this conference. I hope I will not be in a too different perspective of what I saw since the beginning. And so I will mostly concentrate on the question how some numerical models or laboratory experiments can help answer all the questions that you have asked here. So it's a work that has been done in collaboration with a lot of people from geology, from planetary science, from seismology, and also with mathematicians for the development of numerical models. So I can go very fast on the two first slides that are an illustration of what has been discussed here since the beginning, that show clearly that we can observe very similar Levy channel morphology in very different environments. For example, here in Iceland, where we know that water plays a role. For example, here in Lascar volcano for the end of pyroclastic flows, where we know that the gas play a role in fluidization of the material, and also on Mars, as a lot of people have shown. And what is also surprising is when you look at the characteristic dimensions of this morphometric feature, for example, their thickness or the thickness of the levees, they are not very different, for example, for Mars here or for the pyroclastic flow in Lascar. And also, as someone presented in details before, we can also observe levee channel morphology in submarine environment now that we have very high precision data on the bathymetry. And again, you see that the dimensions are not very far from what is observed on Mars or on Earth for pyroclastic flow. So the big question is that can we deduce the physical process during emplacement by looking at the deposits? And I will try to show you that it could be possible with models, but we are maybe far from being sure of the interpretation of the model for a lot of reasons that I will try to explain here. So first, for example, an illustration of what experimental models, so lab experiments or numerical model can bring for information is that, for example, for levee channel flow, we can reproduce the self-channeling and the levee formation with only dry granular material. This is something that has been proved, and I show you an illustration of that. It's a work that was started by Felix and Thomas in 2004. What they did, they released some granular material on a slope, and you see that the granular material choose a given width by itself, so the flow naturally select a width for flowing, and when you cut the alimentation here, then the central channel is dried, and you recover levee channel morphology. And so they did a lot of experiments. So here is the results of some experiments. Here it's monodispersed bits, means that you take particles with the same diameter. And so in gray here you can see the flowing profile. It's a cross section here. And when the channel drains, you can see some levee here and a central channel that is a little bit lower than the levee. If you increase the polydispersity, means you have particles that are more and more different in size. You can still recover the levee channel morphology here, but it's much more enhanced, so you have higher levees compared to the central channel. So you can see that even for dry granular flow, if you change the polydispersity, you can have very different morphological parameters. So what we have shown also is that you can reproduce exactly this self-channeling flow and levee channel morphology with numerical models. So this is an example here. So we simulate this kind of flow. So you can see as a function of time. So first you have the flow that is here. Then you have a thickness that increases as a function of time. And after a certain time, you have a quasi-static flow here with a central channel that flow at a given velocity. And naturally, the model creates quasi-static walls here that select a given width, and this width depends on the initial flux and on the slope of the topography. And at the end, when you cut the alimentation in the model, you recover these levees here bordering a central channel. So as we see from experiments and numerical simulation, by varying the slope, the initial flux, etc., we can see that the morphometry strongly depends on the slope and initial flux. So now if you want to go back to the observation, you see that you have to take into account the real topography if you want to interpret the morphology as well as the initial condition, for example. So what kind of model could we use to interpret the observation? So I will present you very simple equation just to show you what is the basics into this model. I will not enter into the details of the complex equations. So typically, as I said, we have to take into account the complex topography. And it requires to use a lot of numerical grid. So what does it mean? It means that it will take a lot of computational time. And for this reason, we cannot take the Navier-Stokes equation and solve everything. We have to make some approximation. And it's a limitation of this kind of models, as I will discuss later. And typically what people do in geophysics in general, we assume that the thickness of this flow is very small compared to their length. And it's typically true for gullies where you have typically 1 meter thickness and, 500 meter length and also 20 meter width. So we suppose that, and then we make what we say with depth average equation, so we calculate an average velocity, and we make this approximation. And when you do that, you get this very simple balance of forces. So here you have inertia, so it's typically the acceleration of the flow. Here is the driving force, is gravity. So I just put a green square to show where gravity is involved, because it's very important for Martian application, where gravity is different from that in Earth. So you have gravity term here. You have the gradient of pressure. It means that if you are higher thickness here than here, it will push in this direction. And here, this is a very important term, which is the dissipation. So the friction that is experienced by the flow when it travels along the topography. And here, mu is a friction coefficient, which is a tangent of a friction angle, delta. And for example, for granular material, for sand, for example, typical friction angle are 30 or 35 degrees. And glass beads is 20 degrees. And you will see that it's very important in my talk, these parameters. And also something that people neglect, but maybe it's not very important for gullies, is inertial effect, which means that if you have, for example, a hole or here a bump, you will experience centrifugal forces. So in a hole you will be just pushed down, and on a bump you will be pushed up. And this change effective friction that is experienced by the flow. So you can see just a remark here. You have the gravity that is involved in all these terms, because u, the velocity scaled with the square of g, so u square is g. So you can divide all this by g, and you can see that the equations for Earth will be the same as the equation for Mars, and the only difference will be in the acceleration terms. It means that you will have the same deposit, but not the same dynamics. And this is true if the friction coefficient doesn't depend on gravity, which is something that we can discuss if you want. So this kind of model now, it's important because we can take into account the topography. And what I think is very important also is that it doesn't have a lot of parameters inside. Here, the only 3 parameters that we have is the friction coefficient. So what do we need to be able to use this kind of model and compare it quantitatively? I say it here is very important to compare quantitatively the observation and the numerical results. Because as you saw during these past years, we are always able to make something that looks like what we observe. And you can use various processes, and it will always, or not always, but a lot of time looks like. So the thing is that it has to be exactly what we observe. And so what do we need for this? We need the initial and boundary condition. So here, what is the release mass? How long it takes to be released? Boundary condition means, for example, do we have some erodible material on the slope or not? We need the underlying topography, which means we have to define digital elevation models. And I will show that it's very important to have the detailed shape of the deposit, and in particular, the thickness distribution of the deposit. And so this is something that geologists or planetary scientists can provide. And another thing that is completely complementary to that is to be able to have the good rheological behavior in the model, means the good mechanical behavior, as well as the accurate description of physical process in the model. And I should say that all this has had to be advanced. We are not just at the time where all this is solved, and I will illustrate this later. So once we have all this, we can say, okay, which physical process can have to be taken into account in a model to quantitatively reproduce observation. And I will show you, for example, what we can do if we do that. And it's an iterative process, because at the beginning we don't have all in the model, and we don't have a lot of data. So what we can do now with the models that we have and with the observations that we have. So it's a study that we have done a few years ago, and we have tried to simulate a lot of landslide on Earth, on Mars, on other planets. And the idea was to see if there was a general trend that is observed all over the planets, whatever the presence of water, the presence of air or something. So what we have done, we have used our models and tried to simulate the observed deposits. So here you see you have a very small laboratory experiment, so it's centimeter scale. So the color represents the thickness of the deposit. Here it's a real landslide, one that occurred in Hong Kong, 30-meter scale here. And here it's a landslide on Mars, for example. So we simulate all this landslide, and you see that with the model we are quite able to reproduce the area of the deposits and a little bit the thickness distribution that is observed on the field. So we use only landslide for which we had digital elevation model and an idea of the shape of the released mass. So when we do that, what we have, I remember you that we have only one parameter, which is the friction angle. So we use it as an empirical parameter, and we turn the empirical friction in order to be able to reproduce the runout distance or the area of the deposits. So from that, what we can get is this empirical friction parameter as a function of the volume that is involved in each landslide. And what we can observe from that is that even though you have a scatter in the data, you can see that for very small landslide or for granular flow experiments on the lab, you have to use typical friction coefficient of 0.6, 0.7, which is the tangent of 30 degrees, which is the friction angle of the granular material. But as soon as you try to reproduce the landslide with much bigger volume, you see there is a huge volume variation. You can go up to 10 to the power 12 cubic meter. Then you always have to decrease your empirical friction in the model. So the interesting thing is that we have now quantified the fact that we have to decrease the effective dissipation in models, and this is independent on the topography or initial condition or so on. But it's just a first step, as you can imagine, because the most important question is what is the physical origin of this observation? And the next step would be to try or to put into the model some physical process that seems to be able to answer to this question and redo the same thing, trying to see if without turning a parameter, you are able to quantitatively reproduce the runout or the thickness distribution in your models. So just to come back to gullies here, so as far as I understood, the typical volume of gullies is maximum or around 10 to the power 4 cubic meter. Is that about? Something like this, or smaller. So it means 10,000 cubic meter. And if we look at this here, we can see that friction angle, friction coefficient have to be higher than 0.3, for example, if we look at this size. So you will see that I will use this later. So I come back to a study that we did now 6 years ago with Nicolas, and trying to use what we had at that time, which is dry granular flow model, try to see if these models we can recover or reproduce what is observed on Mars. And we try to look at the images and to see what is characteristic of the flow. And typically one thing is a change of direction when you have a change in slope. Only a few degrees of changing slope can change significantly the direction of the flow. And also the most debating, is it possible to reproduce this sinuous character of gullies with this kind of models? And an interesting thing here is also that how the flow reacts to a topography variation, to an obstacle. And this is something that is very useful, I think, for me in geophysics, because of topography, you will really see the hydrological behavior of the flow. And because it's a transient behavior, and it's typical of the rheology that you put in your model. So you can see that here it's an obstacle, and the flow go here and turn around the obstacle and continue to flow with the same, almost the same direction and start to make a sinuosity. So I will show you some simulations that we did at the time. And so here, the first idea was to change the slope. So here you have a slope, and here you have another slope. So it starts like this, and then a few degree change of orientation. And you can see with the numerical models that we can reproduce the change in slope here. And it was in agreement with the change in slope that we observed from the data. But again, it doesn't mean at all that this is dry granular flows, because if you simulate wet granular flows, you will have also a change in slope. But at least with dry granular flow, we can reproduce that. Then, for example, this reaction of the flow when it encounters an obstacle. And here, it's very different. You can see that with dry granular flow, and I show you simulation, but it's exactly what we observe in the lab. If you use dry granular bits and you put an obstacle, you have this kind of behavior. So it means that the flow doesn't go around the obstacle, but you have more this kind of features. So then you can say that at least for this, dry granular flow doesn't reproduce the observation. Now for the sinuosity, so there could be different processes. It can be flow instability, or it can be again reaction related to the topography fluctuations. So we have tried to vary everything in the model, and we never triggered some flow instability, at least with our model. And then we tried to vary the topography. So here you can not see really good, but we had very small fluctuation of the topography. So small thickness and small wavelength variations. And you can see that basically you have the same shape. There is perturbation, but not sinuosity. And the only way with this kind of model to reproduce sinuosity is just to put topography fluctuation that are at the scale of the flow. And when I look at all the picture you have shown, it seems that on a lot of slopes you have deposits of past events with levees and channels. And we can imagine that if a new flow occurs on this topography, maybe it can change its direction accordingly. But it's something that we have to check, and maybe you will tell me that you observe this even in very flat topography. So this is an open question. So from all this, we can say two things. We can say that the only thing that we cannot reproduce at all with dry granular flow is this behavior here. And another thing that I want to discuss is the fact that, as everybody showed, the gullies deposit on slopes that are smaller than 15 degrees, typically, between 10 and 15 degrees. And with granular flow model, if you put inside the friction angle typical of this granular flow, or even the lower friction for higher volume, you are not able to slope on such small slopes. So what it means, at least with regards to this kind of model, is that the flow is fluidized in some way. It could be fluidized with water, it could be fluidized with gas, as I understood is much, maybe people think it's more gas that do that. But it's something also that seems quite strong. You need some fluidized material to reach such small slopes. So this is the first attempt, but then if you say, for example, water play a role, to be sure that you're right, you have to develop a model that takes into account in a proper way the effect of water. So this is the case here. You have to, for example, introduce the gas effect, or also introduce something that plays a big role in granular flow is what we call erosion process. So if you have a granular flow on a deposit, for example, formed by past event, it will make this particle, it will put them in motion, then it will increase the mass of the flowing material, and it can change the dynamics, as I will explain it later. So the idea is that now if we want to interpret better the data, we have to put this in the models, and I could say that it's not an easy way. I will just present some ideas that we are developing now with my colleagues in mathematics, and that we plan to apply to real data as soon as possible. And typically, we want to describe, I understood now that it's maybe not meaningful for mass, because maybe it's not water, but it could be gas. A volume fraction, so you have a volume fraction of solid particle, typically between 0.4 and 0.8, and the rest of your material is made by a fluid. It could be water, or it can be gas, for example. And the way that we are doing the thing is to use two-phase model, and what we want to describe is we will describe both the solid motion and the fluid motion. And we will also, we are describing the interaction between the two. And a very important physical process in this flow is what we call dilatancy. Indeed, what you have when the flow travels on the topography, you have some compression, dilatation of the granular phase. And this will, for example, increase or decrease the excess pore fluid pressure inside the material. And this will have a tremendous effect on the friction that is experienced by the grain. And you can have, for example, complete liquefaction of your flow just because of this process. I just can detail it a little bit. This is something that you observed in transient condition. If you reach a steady state, you will reach a critical volume fraction. It's something that is very well known in critical state mechanics for people working on soil mechanics. But the material will deform completely differently if you start with a loose material, meaning that you have a material that is not dense, that has a volume fraction which is lower than this effective equilibrium volume fraction. Then what happens here? You see that the particles are not really close from each other. You start to shear it, so you shear the material, and in order to deform, this grain will fall in this hole here, and you will have a compression of the material. You see that it will expel the water from the pores, and then the fluid pressure, which is the sum of hydrostatic pressure and when we call excess fluid pressure, this fluid pressure will increase. But the friction that is experienced by the grain is a mu, tangent of delta, remember? The delta that I was talking about before, times the weight of the granular mass. And this is the hydrostatic weight, so this is the weight of the grains balanced by the buoyancy force, by the force of the water. And here you have the excess fluid pressure. So if the excess fluid pressure increases, you can see that it will decrease, and then the friction on the grain will decrease. And it can really go down to zero. And this is something that basically is used to explain the high mobility of fluidized granular material, fluidized by water or fluidized by gas. So they will go further, and in particular, they will be able to go on slopes that are smaller than the typical slope of dry granular material. And you have exactly the contrary behavior if you start by a dense granular material. So you see they are very close to each other. You shear it, so this grain has to move above the neighbor. So then it will dilate. The fluid will be sucked into the granular pores. The pore pressure will decrease, and then the friction will increase. And it will move. It will be harder for the granular material to move. So this is very important and has been shown to be very important in experimental setups also. And another point that I think is very useful and to take into account in the model is what I call the static flowing transition in granular material. It means that when you have a granular flow, not all the mass is flowing. Some part is static and some part is moving. And in particular, when you have erosion, as some French women show very interesting change in morphology, like meandering. So you have a new granular material that will erode the slope around it. And so you have to be able to take into account this static flowing transition. And I show you an example of what it can do. For example, we did experiment where you have a granular column, you release it on a slope, and you release it, for example, on a slope covered by a very thin layer of particles that are initially static, but that can be entrained by the flow. And during the flow, you can see that some particles of the erodible bed are put into motion and this will change the velocity of the flow and the distance that will be reached by the flow. And this is typical results that we can see. So if you do that on a slope angle horizontal slope here, you can see that when you increase the thickness of the granular layer here, it doesn't change at all. So the runout will be the same. Then you increase a little bit, and still nothing happened. But above a critical angle of 16 degrees, which is about half of the friction angle of the particle, then you see that if you have a very thin erodible layer, a few particles here, you can increase a lot the distance or the mobility of the flow. So this is something that could be important if we want to quantify the mobility and then the physical processes behind. And I show you some numerical simulations that we can do now, which models that are much more accurate than the one I presented before, where we solve all the Navier-Stokes equations. So we make no assumptions. We take geological behavior of dry granular flow, and typically what we use is called a viscoplastic law, which means that you have a threshold. If you are under a threshold, then you don't move. If you are above, for example, by gravity or surface gradient, then you move. And you can see that we simulate this granular collapse. So here you have the initial time, the initial column. In pink, you have the initial mass. And as a function of time, it starts to collapse. This is the experiment in pink. And you can see the deposits here. And in blue, you can see our simulations. And the color represents the norm of the velocity. So initially is at rest, then we release it, it starts to flow. And here you can see that not all the mass is flowing. And for example, at that time here, you have only a surface flow. It chooses a thickness of flowing that is related to the threshold into the viscoplastic behavior. So just to explain roughly, what it means is that not all is flowing, and imagine the flow will be on an erodible bed, then only part of the erodible bed will be put into motion depending on the wall force balance and the distance between the threshold. So just to finish, imagine now that you have the very good model, so you have gas, for example, you have grain gas, you have erosion process, everything. Then will you be able to come back to the process by looking at the deposits? So I show you one example where we have a case, a natural case. It's a landslide in Mount Stellar in Alaska, where people doesn't know really if all the mass was initially flowing, collapsing, or if there was some deposit on the slope that was eroded during the flow. So there is two potential scenarios that may explain the data. So here is the scenario that is simulated with the model, where all the mass is released here. The color represents the thickness of the initial mass. Then it flows down the slope, and it makes a deposit here. And the other scenario is when you just take a little part of the mass, here you release it, and it will entrain some material that is already present on the slope. So you can see the dynamics is different. And here the deposits. So now let us look at from the top. And the deposit area that is observed in the field is shown in black line here. And you can see that with these two different scenarios, you obtain exactly the same area of the deposits. So it means that even though you have a different dynamics, if you just look at the area of the deposit, you will not be able to say if it's one or the other scenario. But if you look in the details of the thickness distribution here, in the colors, you see that they are different. So there is a strong signature of the flow dynamics on the thickness distribution of the deposits. So it's a message that people have to make digital elevation model as much as possible with really thickness distributions that will be very useful to test the models. So it's the end, no? Oh. So I will skip everything which is interesting about seismic data, but using seismic data you can do what you want. So, okay, so thank you.
a couple quick questions.
It seemed to me that your models of dry granular flow across plane surfaces, I wondered what difference it would make if you actually constrain a model within a pre-existing channel, because often you have a pre-existing channel. Have you tried this?
Yeah, actually on the simulation that we did of a lot of landslide, there was a lot where we had some channel.
Is the run out farther if you have a channelized system than a
Yeah,
plane
basically, in a lot of, it depends on a lot of things, but basically it is generally longer the run out because you don't have spreading in this direction.
Yeah.
So it means that then, but on the other hand, you have friction along the channels, which reduce a little bit the velocity, but globally, in general, you have further.
You gave us some metaphors, Pals. What do you argue as a erosion deposition argument for the boundary? Like, how do you decide how much entrainment or deposition takes place?
You mean in the model?
Yeah,
Oh.
in the model. You can generate stresses, but how you convert stresses into erosion or deposition?
Yeah, this is a very big issue. So in the models in the simulations that I show, it's done empirically in the way that we put a layer of material and we put some threshold rheology, which means that if the driving forces are higher than a certain threshold, then the material moves, and if it's lower, it doesn't move. It's the rheology of the material. But it's not properly done in this depth average model because either all is flowing or all is static because of the depth averaging process. And we have now new methods that we call multi-layer model, where only part of the material can move. So we don't have to prescribe anything. It just comes out from the viscoplastic rheology that we put in the models. And it's something new in granular physics, where it seems that the viscoplastic rheology that is proposed in the literature is quite able to reproduce this static flowing transition in granular material at first order.
Okay, thank you. So let's move on then. Our next talk is by Hijime Naruse. Dr. Naruse is going to talk about lobate landforms and inverse analysis of debris flow deposits.
Thank you. Thank you, Chairman. I'm Hajime Naruse, a geologist from Kyoto University, Japan. Today I'm going to talk about this title. So, as discussed in this workshop, there are many gullies and lobate deposits in Martian Mars. And often these lobate deposits are interpreted as Martian debris flow deposits. But this is mainly based on the observation. The Martian lobate deposits are quite resemble the debris flow deposits on Earth. This is experiment of debris flow. The mixture of water and sediment released on the slope and flow down to the plate here. This is just 1 meter scale. Debris flow occur by interaction between fluid and granular materials. So if we can observe debris flow on Mars, that may imply liquid water existence on Mars. But the topography of Martian lobate deposit resembles to debris flow deposit on Earth, but there are many other hypotheses to explain this kind of lobate deposits. For example, dry granular flow deposit also looks like the same morphology, the gullies and lobate deposits. And this is pyroclastic flow deposits on Earth, also in the same shape. So, the numerous hypotheses have been proposed to explain gullies and lobate deposits on Mars. So I would like to contribute to this discussion by estimating and compare the rheological properties of debris flows on Mars, my strategy is like this. First, I assume the process is debris flow. This may be null hypothesis. The estimation, then estimate rheological parameter from topography, assuming the process is the debris flow. If the parameters are similar to debris flow on Earth, the Mars debris flow is similar to the debris flow on Earth, that means debris flow on Mars may exist, but other possibility cannot be eliminated. That means other processes can also produce the same geomorphology. So we can't decide the debris flow, this is debris flow or not. But at least if parameters are quite different from the debris flow on Earth, that means flows on Mars are different processes. So this is kind of the null hypothesis. And maybe the discussion possible, but at least I would like to start from the rheological property estimation. The rheological properties of debris flow can be described, for example, like this. This is the shear stress, and this is shear rate. So shear rate increases and shear stress increases. And these dots are experimental results. So mixture of sediment and water shows this kind of behavior. Initially, it's very solid, and suddenly it moves as liquid. So as approximation, we can use this approximation to the rheological behavior. And this parameter is yield strength. Below this, the values, the mixture of solid and water behave as solid. And from this shear stress, the mixture of the sediment and water behave as fluid. Then the inclination of this line is the viscosity. So now we describe the yield strength and viscosity and also density. And that means sediment concentration in the debris flow. Okay, so 3 parameters are necessary. And I employed the debris flow model of the Imran et al. 2001 BIN. This is a simple model and employed assuming the layer average 1D BIN and plastic flow model. The debris flow is separated to the plug flow region and shear flow region, and each momentum conservation are calculated, and also the conservation of the mass is calculated. Yeah? The set parameters like this. This is viscosity and this is yield strength. This is concentration. Then start the calculation. This is blue line is geomorphology, and the red line is the observed geomorphology, for example. Then start calculation. Please click this movie. Yes. The flow down to the slope, and it stopped. So this calculation is wrong, because maybe the parameters are different. So then I change parameter, the viscosity changed. Then please click this movie. Oh, excuse me. Can you click this movie? Oh, excuse me. Can you click? Yeah. Now the flow is down, go this down slope and stop here. This completely matches to the geomorphology. So I assume these parameters are good. Then now viscosity is half, so it's easy to flow down. But this takes a long time. So I would like to do this kind of the parameter optimization automatically. So now I can define fitness of model results like this. This is observed thickness of the bed, and this is calculated bed. And summation of the observation and the calculation drives fitness, how fit the result of the model calculation. And when I change the parameters and get the fitness, then we can define this kind of the plane. And here, the fitness is minimized. This is probably the true initial condition, paleo condition of the debris flow, for example, viscosity or something like that. So this, the parameter optimization is inverse analysis of the optimization problem to minimize the fitness values. But the problem is that this is non-linear optimization problem. So this could show multiple depressions or maybe pre-peaks. So we would like to find this, the minimum value of fitness, but there are many depressions. So finding this global minimum is difficult. So I employed the algorithm, the genetic algorithm for global optimization. I don't have enough time to explain this algorithm, but this is global optimization method simulating the evolution of the creatures. The initial population of genes, that means parameter sets are produced randomly, so it's scattered in the parametric space. And then these individuals are naturally selected. Natural selection occurs, so based on the fitness values. So lower fitness means easy to survive to the next generation. And the next generation is created by the crossover and mutation, and the generation is repeated, this process is repeated, and finally find the global minimum by this algorithm. So this is how the genetic algorithm works. So this is generation, and this is the mean fitness value of the populations. Initially, the random values, random individuals shows higher fitness values, but when generation is increasing, the population is getting optimized to find the global minimum. So this is one result of genetic algorithm, the optimization. These yellow dots are input values for this inverse analysis. Actually, this geomorphology is produced by the numerical calculation. So I know the exact answer to produce this geomorphology. The input values, viscosity is 1,000 and yield strength is 2,000, and solid concentration is 0.7. Then I found the parameter sets to reproduce this geomorphology by using the genetic algorithm. So this completely matches and the parameters of viscosity is almost 1,000 and yield strength is slightly lower than the initial values. And solid concentration is slightly lower than but approximately the initial parameters are reconstructed by this method. So this means if the forward model is correct, we can expect the back calculate from the natural geomorphology to the rheological parameters of debris flows. And I haven't finished the measurements of the Martian geomorphology, but this is just a preliminary results. I just picked the data of the Martian lobate deposit geomorphology. This is blue line, and this is just the averaged topography of the lobes in this region. They're reported by this paper. And the green line is the best fit result of the model calculation. And the viscosity was 800, and the yield strength was about 800, and solid volume fraction is this value. So Now, this is just a preliminary result, so the future, the work is necessary, but just one result are plotted here, and these blue dots are the observation of natural debris flows. Here, this is viscosity and this is solid fraction. So natural debris flows here, and these green triangles are experimental debris flows, so lower viscosity, and these are natural, also experimental debris flow of the very low, fine-grained materials. And this is hyperconcentrated flow. It's a very high concentrated river flows. So this means that our preliminary result is quite resembled to the similar region on natural debris flows on Earth. So the debris flow, from this preliminary result, debris flow can produce Martian lobate deposits. And the rheological properties of other type of flows, for example, frozen granular flows, should be examined as a future work. So this is summary and future works. Inverse analysis of gullies and lobate deposits can estimate rheological properties of debris flows. And preliminary result indicates that the Martian gullies and lobate can be maybe produced by debris flows, the water-saturated debris flows, the intermittent existence of liquid water. But the future works are necessary. Topographic measurements and more comprehensive analysis of debris flow deposits. Maybe I will change the more complicated physical models, or accuracy and precision of analysis should be verified by experiments. Also, this is necessary. And other types of flows should be also examined to compare which is the more plausible to explain the geomorphology. That's all.
Questions?
A lot of the more recent models for debris flows account for the pore pressure varying. So, so you can't have a constant viscosity or yield stress. It depends on the suspension state of the material. And these constant models, people have had a lot of trouble fitting them to things on Earth, and that's why they're using these other models. So I was wondering, whether you're going to try to look at these more sophisticated models or not.
Yeah. Okay, I understand. So you mean the yield strength and viscosity are constant in this model, but it is not natural.
Yeah.
Okay. Yeah, that's true. So probably I need to change it. This is just south line, so maybe but yeah, I'm afraid also the parameters, if parameters are increased, so the optimization also becomes difficult. So best benefit and the risks exist, but yeah, that's true.
If I understood it correctly, you were optimizing your 3 parameters to give your best fit model result to an average of Levy's field data.
Yeah.
So I just wonder if you went to the original data of Levy, what range of parameter values you would need to explain individual landforms?
I would like to do that. I've said it, but yeah, each debris flow has different property maybe, and maybe I can distinguish 2 types or something like that. Yeah.
And how did you determine where the flow starts from?
Sorry.
Where the origin, where?
Ah.
You have a profile.
Yeah.
And then you have the deposits at the end. In the data you were fitting to from Joe Levy's work, how did you decide where the flow started?
I suppose it starts from the alcove, the middle part of alcove.
It's got a lot of promise, this method, since what we have is the morphology. It's nice to get some constraints, some way of getting constraints on the rheology too.